Yeah, also in France actually. I think it's something related to languages. That we struggle with. Yeah, a lot. Yeah. Yeah, because we need to explain. Okay, today's speaker is Gayandhi De Silva from the University of Sidney and Australian Telescope Observatory. Gayandhi was an undergraduate student at Monash, which is in Melbourne, and then she moved for her PhD to Stromlo under the supervision of Ken Freeman, working on chemical abundances of overcluster stars. After that, she took a Milky fellowship, first in Chile and then in GALactic. Then she moved back to Australia in Sydney as the HERMES project scientist, and now she has a joint position, AEO and the University of Sydney, working on Galah. So today she's going to give an update about this survey.
Thank you, Valentina, and thank you for hosting me. Can you hear me at the back? Yeah, okay, perfect. Yes, I'm here to tell you a little bit about this survey called Galah, and since you're not Australian, you're wondering what a Galah is. This is a Galah. It's a toy Galah we have. That's why it's all pink and gray color codes. Okay, so nice to be here. So basically, I'll spend a bit of this talk in two parts. One on the background on galactic archaeology, and especially on this thing called chemical tagging, what that's trying to do. And then the second half, I'll talk a bit of the instrument and then a little bit on the actual survey and where we are going with it. So I guess the big picture we are trying to address, we're trying to understand is our galaxy, how our galaxy formed, We have, as you probably know, a broad idea of galaxy formation from cosmology, from lambda CDM. We have a hierarchical formation, we have mergers, we have accretion, we have the in situ star formation, there's inflows, outflows. There is, of course, then stellar migration, stars that move with the spiral arms and other dynamical processes. So these are the big, the overarching processes. But we know most of this, but we don't know the details. So in the bottom put here, what we want to know is the positions, velocities, ages, and abundance, not just the metallicity, but individual chemical abundances for individual stars. So for this, we have to come to our galaxy, not to do high redshift work, extragalactic work. So that's why the focus is on the Milky Way, and then we can, once we do this study, then we can expand out to other galaxies. So if we have this information, we can then infer the chemical evolution, the chemodynamical evolution, look at the star formation history, and of course then subsequently do things like the stellar yields, the initial mass function, and then get an idea of how things are distributed with age. So age with abundance and their motions and positions. So that's just the big picture, big goal. We know the components of the Milky Way, of course, but when we say galactic archaeology, or the archaeology part of it at least, name comes from the idea of looking for these building blocks, if you like, the fossil remnants of the original star-forming groups or aggregates. So I think the name galactic archaeology itself was put forward by Ken Freeman and Josh Bland Hawthorne, although the concept has been there for much longer. So this is the schematic of the Milky Way. I think it's mostly explanatory. There's a dark halo. I'm not talking about dark matter after this slide, no more. And there's everything else is baryonic matter. So the bulk of the mass is of course in the disk, in the thin disk and the thick disk. That's two distinct components. And what we want to know really, where most of the mass is in the disk, we want to identify these fossil groups and what happened inside this disk, because this is where most of the baryonic matter is, and of course a disk is what defines a disk galaxy, so obviously we need to understand the disk. The halo is of course important, but it is, I would say, easier because things are much more longer time scales and preserved. And these dots are the globular clusters, which I'm not going to talk about at all in this talk. So, okay, what we want to do is then find out how the stars came into these two components. So stars are formed in groups, in clusters. They don't just randomly appear here and there. So there are stars in the galaxy. It should have come from a cluster at some point in its time. So we have, these are open clusters that I'm referring to, not the globular stars that form in the disk. They are a single age, single burst of events, so they are chemically uniform. You expect it to be reflecting the material from the gas cloud from which it was born. But the problem is they are short-lived. They don't stay in its family for a long time, and there are only a handful of open clusters that are more than 1 giga a year. So before that, these clusters disperse. But they don't, the cluster evaporates, but the star doesn't evaporate. The star is still somewhere in the galaxy. So we should be able to trace these individual stars that's in the Milky Way right now. We just need to find a way to tag it, find a way to trace it. So how can we trace these original clusters? You can use kinematics, the motions. That's one way of doing it, but it is a bit unreliable for older stars because you can imagine the disk is very active. It's a lot of processes going on. There are molecular clouds. So if you measure the motion of a star now, that its current velocity, current direction. It could have had some other event before we got to it. So we're not tracing back to the original velocity. So it's a bit limited in this sense. So the chemical information in terms of what we measure from stellar photospheres, it might be a bit more longer lived. So this is where we are going with this idea of chemical tagging. So to use the chemical information as a tag to this conformation size. And this has some assumptions, of course. The assumption is that all stars are formed together and they have the same chemistry. Because if this doesn't hold, we can't do this at all. And that the chemical elements that we are measuring don't change during the stellar evolution process, because this is also, again, we lose the information. I put a star there because some elements do change depending on the type of star. For example, giant stars, there is mixing and then there's breakup. So the lighter elements will change with stellar evolution. So, but for the heavier elements, certainly heavier than iron, heavier than oxygen, you don't expect this to change in the present measured abundances. So if we have that, then we can do this matching, not just the metallicity, looking at least 10, 20 elements. So then if you get something like, let's say, equivalent of a DNA pattern or something with stellar abundances, and if you get two identical ones, then you think, okay, they should have come from the same birth site. So this can help tie down quite a bit of the unknowns right now. So if we can regroup a sample of stars in the Milky Way into a cluster, now you have a constraint on what is now a hot topic, is radial migration, stars that move from the in to the out or out to the in. How this would have happened, there's a lot of theoretical push for radial migration, but observationally evidence is not so strong yet. So if you can reconstruct the group and now look at where these stars in the group are now, then we can get a better understanding of migration processes and also the effects of the bar and the spiral arms in terms of how they move the mass around the galaxy, and also get an estimate of the earlier mass functions of star formation. Was it massive, was it less, the fraction of gas mass and so forth. And of course there's a whole heap of stellar physics that will come through from nucleosynthesis processes, the yields and so forth. So if we do this, it's a very powerful tool. Now, chemical tagging is a relatively new term, I would say, probably about 10 years. I mean, I did my thesis and no one else knew what chemical tagging was, so it was just a starting time. So I want to just quickly go through some examples of what I would say early attempts at chemical tagging. So what we did quite a lot was looking at dispersing clusters. So these are star clusters that have already started dispersing. So the stars or the members are all over the sky, but they still have a common motion. So they haven't lost the kinematical information. If you look at their galactic motions, the U, V, W motions, you see that they come in a common velocity space. So you can trace these stars of, for example, this HR 1614 or the Wolf 360 group. The stars are not a cluster, but they are co-moving. And when you look at the chemistry of some of them, we find that they are just as uniform as an open cluster is. So that tells us that, okay, these are now all the sky, but they should have formed at the same time. And then there are these cases where you have the cluster like the Hyades, and you have a huge stream that are mixed up, but chemically they are very similar. Same as with the 231 and the Argus association. The Argus is a stream, 2391 is a cluster, and they are chemically identical. There are other cases. So remember I said about dynamical motions not being reliable. So there are these other cases of what I would call a stream that are co-moving. So when you look at the velocities, they're the same. But when you look at the chemistry, it's a mixture of field stars. So it's a heterogeneous chemical signature. So it's not a cluster, it's not a dispersing cluster. So examples, the Hercules stream, and there are, I would say 90% of all streams that are in the local samples are these dynamical streams. It's not a cluster. The two figures are just, this is from the Hyades. The cluster is here, but the marked dots are members which are up to about 500 particles. So this is X, Y, and X, Z. And this is just to show what I meant by homogeneity. So this is a delta. It can be any abundance, not just iron. Versus the different stars, the temperatures, and you see that they are within about 0.05, 0.02 dex, depending on your errors. Certainly within your error bar. So that's the expected level of uniformity. So in this case, we had help. We had help from the motions to distinguish what is a cluster and not. This is another example of early tagging, but now going blind without any other kinematics. At that time, this work was done, 2013. The only publicly available largest uniformly analyzed data sample was 700 stars by Bensby et al. And what we did here was just input the abundance catalog, nothing else, no other information, and see if we can chemically identify groups that are similar from these 700 stars. That just a flow chart showing the method. Basically what we used was a chemical difference metric. It was just calculating how similar two elements are for every combination of stars in that 700 sample, and then decide on a limit where things are homogeneous or not, depending on open cluster level. And then you say, okay, we have some confident pairs, and then that would effectively be our cluster. If we do this for the 700, what we found was quite a lot of groups. Not sure I fully believe the details of this, but I don't know if you can see. So this is this delta C level, so effectively the measure of homogeneity plotted against here, so the number of stars per group for the different groups. That's this arbitrary, so maximum number of stars versus the minimum number. So we had about, I would say, 5 to 10 clusters with more than 10 stars in the group. So once you get down the tail, it's a bit iffy. So and the two colors are for a tighter level of 90%, and the other one is at 68% probability level. So this was interesting. This was just the first, walking in the water for the first time. But we were quite happy with this because we got chemical groups, some which are believable and some which are a bit harder to believe. But what we also found out in the process, that suddenly you have a field star sample that's in a group, it's in a cluster. So everything you can do with a cluster, like fit an isochron, you can do it now. Before you only had the individual stars, so we're doing a better job with ages by the chemical tagging process. So that's just some examples. I mean, sometimes you get lucky here, like the 6 stars are just in the right spots. Also to notice that when you look at the velocities now, you go back and look at the velocities of these chemical groups, it's all over the place. So it's not necessarily co-moving as we expected. And this plot shows with our new ages for the alpha abundances, so this is magnesium, aluminium, calcium abundances, and iron abundance. The individual sample of 700 is actually in little gray dots. I don't know if you can see at the edge here, where the ages are not so well constrained, and the big dots, the gray dots, are the 68% confidence groups. And I would say that, doing this chemical tagging hasn't screwed anything up. It's pretty much following the same trends that you expect. So the older disk stars here, the other ones just on this side, and maybe it's a bit tighter now than the field stars, and the ages are still better, I would say. Also, now that the field stars are in groups, you can do things like look at the velocity dispersion, which you can't do if you don't only have one star. So here with age and the sigma dispersion, you see maybe the spread is larger at higher ages, which you'd expect with time. Things are being scattered more. That's just an example of what you could do with chemical tagging. Other thing that more recently Alice Quillen and collaborators did, they picked 6 of the largest groups we found here. I think it's, yeah, so the 3 of the largest here and the 3 largest groups over there. And they did a probability study of what would be the parent group. So remember, of 700 stars, we only had like 10, 20 stars in these groups. So if this was selected within our small horizon of this 700 stars, which must have been 100 parsecs, what would be the parent cluster? What would be the bigger one? And the numbers came out to be very large, at least 10 to the power 6. To be a parent group within the whole galaxy, and we found that if that is so large, it might be that we are tracing populations which are multiple populations. In other words, same chemistry but not one site. It could be multiple sites with identical chemical evolution. So the word is coeval, not necessarily co-natal in the same spot. And also then if you look at the angular momentum and eccentricity of these tagged stars, you find the older ones have a larger spread. So that's indicating that there is more effects of this migration and mixing in from the thick disk, the older stars, whereas the younger clusters are better behaved and seem to be less impacted by any mixing. That's kind of what other people kind of getting as well, but this is a hot topic. This sample is not big enough to address that issue. So going back to this question of chemical tagging, there are several camps, people who think it's definitely the best thing to do, others who are a bit more skeptical. I guess observationally from open cluster work, it's quite clear that open clusters are uniform. There is nothing to prevent that aspect of things. Theoretically, you see this from the models that there's a lot of turbulence going on in the gas clouds. So even if it is a low mass clusters, this latest one from Feng and Kamphaus say that even for like an OB association, you should have chemically uniform material. So that's positive. Now the other thing for this tagging to work is how many dimensions, how many components in the chemistry. So you have 20-30 elements, but they're not all independent. So depending on the supernova types, you have let's say the iron group will all be the same. So iron, nickel will be the similar abundance. So the dimensionality of the chemical space is important. Not so much work, I guess, has been done on this. The number of components depends 6 to 9 depending on the sample, because if you look at local field stars within the solar neighborhood, you get less. If you look at open clusters which span larger radius and age, I guess, you get more, you get 9 from there. So it's a bit of a chasing your tail experiment, because you need to have a sample to be able to tell the dimensionality. So without sample, it's harder to predict it. Other things against chemical tagging would be some of the papers that show that it's difficult to differentiate between evolutionary stages. Say this work by Blanco Quaresma, for example, they tried chemical tagging of open cluster stars. What they did was they took abundances from the literature and they uniformed it somehow, I think, or they reanalyzed the data, and they put it into one sample and tried to tag them again, and they found that they were tagging the same cluster into 2 groups, like dwarfs and giants. So there were some issues that they raised there, effects of diffusion and other mixing effects. they might turn up, but anyway. Just more recently, actually end of last year, there was a paper from Hogg et al. Using the apogee data and with, oh, the plot's a bit weird. Okay, not sure what happened there. And okay, you can't see. There's a dot over here, and there's a dot over here. This is what they found as the abundance, what we call it, density is what they called it. It's the number of stars, no, not number of stars, number of uniformity, if you like. And what's the number of stars in here? So from the apogee data, they recovered some clusters just using a k-means labeling and tagging. So there is some positive results as well. So these are globular clusters, of course, and they didn't label them beforehand. Anyway, that's just kind of the little overview on chemical tagging options, but I guess now I'll move on to the second part of my talk about Galah. So the apogee data had about, I think, 12 chemical elements, 12 to 15 perhaps. So we move on to what we are trying to do for 1 million stars in Galah. Okay, so a very quick overview. The instrument that Galah is using is called HERMES. It's a long acronym, but HERMES is the instrument that was commissioned in end of 2013, 2014, on the Anglo-Australian Telescope, which is in Coonabarabran in Australia. It's a 4-meter telescope. HERMES was, the driver for HERMES was to do this survey. If we want to do 1 million stars at high resolution and high being about 25 or 30,000, get all of these individual parameters, and more specifically to get the chemical elements, because that's what's probing the chemical tagging method. And I highlight that the number of stars and the resolution makes it quite unique and ambitious. Here's some stuff about HERMES. So the instrument, like I said, was just only relatively recently commissioned. It's a 4-armed spectrograph. It's got 4 individual VPH gratings. So basically, it's a pretty big instrument. It's about 3 by 4 meters, about half of this room here, and it's fed by a fiber system, which I'll talk about later. So 4 individual cameras, 4 channels, 3 beam splitters in it. Not sure what else you need to know, but other thing is that the 4 channels are very narrow in wavelength range. It's 200 angstroms or so. So these channels were picked specifically to get all of those chemical elements, because I guess you know with the gratings you can get their wavelength efficiency to be high enough only in that narrow region, so you had to tweak to get it in the right spot so we can cover enough spectral lines. But that's what we ended up with. We all agreed to. It's fed by an existing fiber positioning system that's on the AAT. This is now getting a bit of a older thing. It's still very nice. It's a little fiber positioning pick and place gripper. So here you see the plate, one of the plates. There are 2 plates on what's called 2DF. It's the 2-degree field spectrograph. It's 2 degrees on sky. One of these plates here is, you can maybe just see the buttons, little squares in here, and the fibers normally live on the edge, and the little gripper rubber will pick and place it into whatever configuration you want. There's a total of 400 fibers. 8 are used for guiding, so we have 392 that we can observe in one go. There's another plate on the other side, so there are 2 identical plates basically. So you can observe on one side while the other side is configuring and arranging for the next observation. So you spend all night between tumbling the two plates around. So that's a picture of the AIT. The top end, that barrel is where the two plates lie and the robot sits on top there. So this point is pointing towards the telescope. We'll be observing, the top will be configuring. And there's the massive fiber cable that runs down the telescope and goes into a Coude room, which is where the instrument lives. So there's the existing instrument, the older instrument, A omega, and HERMES is basically positioned just next to it, and it's in a stable, temperature-controlled clean room. This is HERMES after it's assembled. So that's the fiber cable coming in, the collimator, and then the 4 channels, the 4 cameras over here. So it's relatively stable, assuming no one goes in and plays with things. So it's working pretty well as designed. All right, so those 4 channels. What did I miss? The spectral resolution is 28,000 roughly. And the 4 channels give us elements, spectral lines to measure the chemistry in these 29 chemical elements, and they span at least 6 what we think are different processes. Okay, so we have around 350 to 390 simultaneous observations. There's just one little cutout of the H alpha region, just to show what it looks like. It's a lot of data. So we have 4 CCDs, so we use up several gigabytes in any given night to fill up all the disks. And once you extract the spectra, this is the sun. It looks a bit like this. So this is the bluer, we call green, red, and infrared. It's not quite infrared, but anyway. Regions. So the spectra is quite nice at the resolution. Okay, now moving on to Galah. Specifically, that's the instrument. The instrument is available for general use on the telescope. It's not exclusively for Galah. It's just a general use instrument. We have for the Galah program, we are observing every field so this one shows little dots in gray. They are all possible observations for the survey. The little gray, the light pink and the pink dots are what we've already observed. This is a bit old. This is only until I think January last year. And this is the K2 fields. If you're wondering what that follows the ecliptic, it's there's another supplementary program that's following up the K2 fields, so we can get the parameters to complement the astroseismic data, which is also co-shared with the Galah program. So that's also in there. I guess this is a bit of a whinging plot. The original plan when HERMES was built was to have 100 nights per year. We didn't quite get that. We got a 70% allocation. The weather at the observatory is not ideal. 1/3-ish is lost for rain or clouds or bad seeing and whatnot. So our data rate, which was expected to be that many stars per semester, is just about half maybe. But anyway, we keep going. We have time until this time next year, basically, to finish or to get through as much as we can, or reapply to the TAC again. But anyway, we have still quite a large sample. So right now we have about 350,000 spectra of individual stars. So I think that is the largest data set of high resolution spectra ever collected. So it's pretty good. And what are the data like? Just a very quick plot of the signal to noise. So that's the signal to noise versus the cumulative fraction. In the blue, of course, you get less signal. That's just the way the blue, not so blue. And in the red and the infrared, most of the stars are above our threshold. Okay, and that's a little movie on where we are looking in the galaxy. The blue ones are the dwarfs and the red ones are the giants. This is photometric distances, estimates only, but for a visual it's quite nice. It shows where we're looking. The higher density is actually the dwarfs. It doesn't look it, but there's more dwarfs in there than there are giants. That's kind of our signature to date, or since last year. And the survey, so the selection is pretty simple. It's just a magnitude selection. There is no other color or any other constraints, between 12 to 14 in B. We use 2 mass as our input catalogs together with APAS and some PPMXL. This is a theoretical expectation of our distribution from this Galaxia model. It will be mostly dwarfs in the thin disk, which is where we were aiming for. A few giants and few fractions in the halo, but mostly thin and thick disk. And this is a simulation of what you expect in the distributions, but more or less what we expect. Okay, so once we have the data of the telescope, when the fun begins, I guess. We have a relatively well thought out and planned input catalog and selection from the input catalog, because we had to select these 2-degree field observations for the fibers. So there's a Ops Manager software which does that, it picks up the density of the stars in the region, and it makes these circles that we can then configure on the robot. Once the observing comes, there is a reduction pipeline. We had multiple reduction pipelines. The one that got through was an IRAF-based pipeline, and that does all the basic cleaning, biasing, flat fielding, and eventually extracting the spectra. We do a very first pass spectral matching software called GUESS, which is overlap spectra. Get your basic parameters. And then the heart of the survey, I guess, is your spectroscopic analysis. You want to get these many elemental abundances, temperature, gravity. So I'll talk a bit more on that later. But then eventually you combine the input and the output, and you have your data release catalog. Okay, so the data analysis part, it's mostly based on SME. Familiar with SME, by Valenti and Piscanov, can't remember the reference originally. But that's the main analysis software, and it's headed by Martin Asplund and Karin Lind, who are looking after that part of it. But this takes time. For 300,000 stars, it would take about 30 years. So what we are doing is we are using this data-driven approach called the Canon. There are several references on the Canon. I guess Apogee has used this as well. Canon, I don't know much about the physics of the maths of how the Canon works, but basically it is something that needs a training set. It needs to be told what a spectrum looks like and what its properties are in terms of temperature, gravity, metricity. And then it would learn, and every time you give it a new spectrum, it would classify it. That's kind of how I understand it. But the practical part is fast. It takes seconds to run it on the Galah spectra. Once the training is done on a significant sample, we have about 30,000 in the training sample, then this takes, I guess, less than a day to get the rest of it done. So the results here is from the Canon on about 200,000 stars. Not sure what more to say about it, except that we're getting results, which is good, and it looks about right. So Galah is not the only survey doing not the only large survey. There are several complementary surveys. There's the Gaia ISO project that's on the VLT. It's complementarity in that it is a lot fainter. I guess there's only a little overlap between the faint end of Galah and the bright end of Gaia ISO. and that's targeting mainly thick disk and the halo and also star clusters, open clusters. And then there's apogee, which is not now in the north but also coming up in the south, which is in the H band. So, and it's looking at low latitudes, which we are avoiding, could be dust. So there is that complementarity there. I guess we have more overlap with apogee than with Gaia, so but people are talking to collaborate, so we can cross match and all that. Of course, the obvious overlap is with Gaia. I guess we'll have probably every single star in Galah will eventually be in Gaia data in the subsequent data releases. Maybe at our magnitude limit we are getting perhaps the best of the Gaia accuracy. So ultimately, the summary is that if we want to do an independent check on these chemical tagging groups with independent ages, this would be where it'll all come together. We had the very first data release earlier last year, and that was overlapping with the Tycho Gaia catalog, and we had about 9,000 stars overlapping over there. In a practical benefit, of course, once you had the T-gas overlap, we could fix up some of these painful things like this upturn in the stellar parameter, which is known by most spectroscopists. We have this issue where you can't get the gravity right. So once we had we could tie down log G's from Gaia data, you can kind of recalibrate things, and this is pre and post calibration. Maybe things are a bit tighter now, and we don't have this tail. But of course, the analysis is always improving. It's not once done. It's something that goes on forever, I guess. Always getting better. Also, when you have a large survey without any color cuts, you get all sorts of other weirdos, peculiar stars. This is just some of the examples that the collaborators in Slovenia are working on, looking at H alpha emission and also in H beta, and these spectroscopic binaries, double line stuff. There's a whole heap of weird things and stuff that we might not end up using for chemical information because they're too hot or there's other features. But again, it's a lot of other science to be done with the data set. Okay, and I think I might. Okay, so there's some very first abundance comparisons with some theoretical yields. This is done by Chiaki Kobayashi from her models, which are in blue, versus the observations in white. Now I don't know which one is right or wrong, whether the abundances or her models, but yeah, it's just a very quick look, and overall some things are matching up quite well, some things are not. I'm not sure what's going on in titanium, but we do have abundances for about 29 to 30 elements. That's it. So of course I have to acknowledge all of the rest of the Galah collaboration. In principle we have about 70-80 people, but the bulk of the people who do the work are about 10 to 20 people. So specifically Ken, Joss, Martin, who really put everyone together and get things going. Okay, thank you.
Questions? We need to use these parts because otherwise everyone has
Yes, if the galaxy build up as a series of merging events, what picture can come from this kind of study?
Yeah, I guess if it's something that's secreted from elsewhere, so dwarf galaxies and other merging, I think that will be, when we do the chemical tagging, they will stand out easier, better or more obvious than the in situ star formation, because they will have a different star formation history compared to most of the in situ ones. So maybe there'll be more metal pool, I guess. Dwarf galaxies are, I'm not 100% sure of the field, but I think we'll definitely recover a lot of those accreted objects, even in the disk as well, if that's the case.
From one of your biographs, the one showing the Milky Way with the line of sights of the Galah Survey, I got the visual impression that most of the targets were in the halo. But from your table, it looks at this, only 1% are in the halo. So you confirm that there is 10,000 in the end, there will be 10,000 halo stars in the sample.
Yeah. It's just a visual thing. I think the density is not shown very much in that movie because the blue ones, we have more dwarfs, for example. The blue doesn't strike up.
Yeah, the other thing is, since our galaxy, all in all, contains of order of 200 billion stars, having sampled only 1 million, that is a kind of small fraction, there you should be able to infer what is the minimum mass of the potential original cluster that you could recover as a debris.
Yeah, that's right.
Did you make what is this?
I don't know
mass?
the minimum mass. I mean, the thing is, the larger the sample, the better you can constrain the minimal mass. So I think there was a study by on apogee data that they can't find anything. They're not sensitive to anything about 10 to the 7 solar masses. But I don't know whether that is limited to the sample or whether it is limited to the technique or something like that. But so something that the reason I didn't justify the million stars. So if it is, I don't have the plot here. So the number of, okay, there's so many assumptions. Assuming things are mixed uniformly, and the number of chemical cells that we can tag to is 7, let's say. So that's the number we use. You need 1 million stars to get down to 10 to the 3, 4, that level. There's several papers by Josh Blind Hawthorne on these numbers. So if you go for with 1 million stars, we should be able to get to that kind of masses. But whether we will recover something of that, we don't know yet. So we'll be able to tell. But yeah, that's the goal. Something like that, 10 to 3, 10 to 4.
Did you find any systematics in the classification between SME and Canon?
Yeah, I have the plot some. I can show you later on if you want. But there is not so much a systematics, but there are at the hotter and the colder end, you start to see a little bit of deviations. But overall, I think if you were to take the mean number was 100, 150 Kelvin in temperature, thereabouts. So I don't know so much about, I mean, Canon is relatively new, this method. So in principle, it would increase the accuracy of SME rather than just propagating it alone.
Just a comment on that. You will generally not have systematics by design because the Canon is trained on the SME analyzed sample. So
yes and no, because it depends on the size of the
that is true. That is true. But generally speaking, that is not a good test of how the Canon is doing because by design, if you give it a training set, it will retrieve the same average abundances. But that doesn't mean that it gets the correct abundance. Not because it's not good, but because it's still work in progress. It's still a new thing, and it's still very much work in progress.
Yeah, no, I understand, but we use the same system in Gaia.
Mhm.
Still, we can see systematics.
Okay.
Because it depends on a lot of factors. What is the size of the training data?
Yeah, of course. That's yeah. How much dimension it spans, and et cetera, et cetera. Of course, yeah.
It's not obvious, yes.
Yeah, I can show you some of the stuff earlier, but yeah, there was some stuff that was, okay, I can't figure out where it is now, but anyway. But so the training sample right now that has been done has only been for 30,000 stars. And also then, I didn't mention, but originally the can was only for parameters, but now there is work showing they can do the individual elements as well. Then you would need a larger training set to cover the abundant space. So if we eventually get to 1 million, maybe we have to do, and we want to do 30 elements, we might have to do 100,000 stars training set.
At least.
Yeah. So you have to weigh the time, cost, and everything else.
Thank you, Aya.
Thank you. I showed you this, right? The comparison. I showed it to you yesterday. This must be. Yeah, this is the 150.